Hi everyone, welcome to our video recording on section 2.5 dealing with limits at infinity. In this video, we're going to be taking a look at limits at infinity and horizontal asymptotes. Now, in the previous sections, we worked with limits where the y values were becoming arbitrarily large, either in the positive or the negative direction. So for example, if I gave you the limit as x approaches 3 from the right for 2 over x minus 3, we would get infinity. These ones were infinite limits. In this section, we're going to take a look at what happens to the y values when it's the x's that are now becoming arbitrarily large, either in the positive or the negative direction. So these are the type of problems that we're going to be dealing with. The limit as x approaches infinity for f of x, or the limit as x approaches negative infinity for f of x. These are known as limits at infinity, and they can help us determine the end behavior and horizontal asymptotes for a function. Let's go ahead and begin by analyzing the behavior for the given function, where we have f of x equals to x squared minus 1 all over x squared plus 1. And let's see what happens as the x becomes larger and larger. Well, we get to see in our table of values here that as our x's are getting bigger and bigger, in other words, approaching infinity, I did include the plus or minus, so you could have also been approaching a negative infinity. The y values, though, they're not getting bigger. In this particular case, though, it seems like they are approaching a particular value. And which value is that? Well, we can see here that it seems like the y values are getting closer and closer to 1. Now, this is also illustrated graphically with the graph of the function. We get to see here that as our x's are getting larger and larger in the positive direction, in this case the x's are going to infinity here, the y values, they seem to be getting closer and closer to a 1. And if the x's get larger and larger, but this time around going in the negative direction, well, the y values, they're still getting closer and closer to the y value of 1. So for this problem, we can say here that the limit as x approaches infinity for x squared minus 1 all over x squared plus 1 is equals to 1. And the limit as x approaches negative infinity for x squared minus 1 all over x squared plus 1 is also equals to 1. Alright, so now let's go ahead and begin by discussing a few definitions. Alright, so what is the definition here for a limit at infinity? Alright, so let's say that we have a function f defined on some open interval from a to infinity. Then, the limit as x approaches infinity for f of x is equals to L means that the values for f of x, they can be made arbitrarily close to L by having the x be sufficiently large. Now, the definition for a limit at negative infinity is very similar. So let's say that we have a function defined on some open interval from negative infinity to a. Then the limit as x approaches negative infinity for f of x is equals to L. This means that the values for the f of x, they can be made arbitrarily close to L by having the x be sufficiently large, but now in the negative direction. Alright, so now let's go ahead and begin by discussing a few definitions. Alright, so what is the definition here for a limit at infinity? Alright, so let's say that we have a function f defined on some open interval from a to infinity. Then, the limit as x approaches infinity for f of x is equals to L means that the values for f of x, they can be made arbitrarily close to L by having the x be sufficiently large. Now, the definition for a limit at negative infinity is very similar. So let's say that we have a function defined on some open interval from negative infinity to a. Then the limit as x approaches negative infinity for f of x is equals to L. This means that the values for the f of x, they can be made arbitrarily close to L by having the x be sufficiently large, but now in the negative direction. Alright, now before we move on, I want to take the opportunity to talk about infinity here, especially now that we've seen limits at infinity and infinite limits. Remember, infinity is not a number. We cannot perform arithmetic with it. However, we can work with the following ideas. Let's say that we have a to be some real number. Well, I have a real number plus infinity. What we're saying here is that we have a number plus something that is arbitrarily large, so we get something that's also arbitrarily large. Now, if we have a number and we subtract something that's arbitrarily large, well, we have a negative number that's arbitrarily large. If we have a number times something that's arbitrarily large, then we're getting a number that's also arbitrarily large. And so a number that's arbitrarily large plus another number that's arbitrarily large, well, you can expect that yes, we have something that's arbitrarily large. And last but not least, a number that's arbitrarily large times another number that's arbitrarily large, well, we get an arbitrarily large number. Now, all this might seem a little bit intuitive. However, we have to be careful with the following. If we have an arbitrarily large number minus another arbitrarily large number, what do we get? Do we get 0? Do we get an arbitrarily small number? Well, what do we get? Well, we actually don't know what we get here. Now, we're going to be talking more about these concepts later, but for now, I want you to know that, yeah, we cannot do much with them yet, because these ones are also indeterminate forms. Another indeterminate form here is infinity over infinity, something arbitrarily large divided by something that's arbitrarily large. This is not 1 either, this is not 0, this is not infinity. Same thing here with the idea of an arbitrarily large number raised to the 0 power, or 0 times something that's arbitrarily large, or 1 raised to some arbitrarily large number. Now these ones here will come into play when we talk more about limits, but for now guys, just careful with these ones. The ones above, this ones here work just fine. This one's gotta be careful. Okay, now again, we'll see how we can deal with scenarios like this down the line, but for now, let's go ahead and move on to horizontal asymptotes. So we've probably seen horizontal asymptotes in a pre-calculus class, but now we're going to be looking at them through the lenses of calculus. Alright, so let's go through the definition. The line y equals to b is a horizontal asymptote if either or both of the following statements are true. The limit as x approaches negative infinity for f of x is b, or the limit as x approaches infinity for f of x is b. Now, I want you to know that the graph of our irrational function, it may or may not cross a horizontal asymptote. So you just got to be careful there. I didn't mention it here, but we cannot cross a vertical asymptote, but we may or may not cross a horizontal asymptote. Now, with that out of the way, I want to take a look here at example 1. And for this one, I want you to use your previous knowledge about functions and their graphs to find the following limits. Which ones have a horizontal asymptote? Alright, since we're going to be using the graphs primarily to figure out what is happening as the x's get arbitrarily large, I gave myself here a couple of grids. Now, if you don't want to use a graph, that's fine, but I do want you guys to get comfortable identifying the common functions. That's the reason why I'm choosing this exercise like this. Alright, so let's go ahead and begin with the first limit. What will be the limit as x approaches infinity for x cubed? Alright, now you might remember the cubic function to look something like this, kind of like this squiggly here. Now this is just a sketch, it's not going to be really good guys, but well, I think it came out decent. Alright, so here's our x, here's our y-axis. Now as the x gets really big in the positive direction, what is your y value getting closer and closer to? Well, in this case, if you picture 1,000 cubed, it's a really big number. So yeah, we're not really approaching anything. We just illustrated here by the graph. It's just going to keep on getting bigger and bigger. So this limit is going to be infinity. Okay, now what about the next graph? What would be the limit for the cosine function as the x gets larger and larger in the positive direction? Alright, so how did the cosine function look like? Well, we made a sketch in the previous video, so I'm not going to go into a lot of detail with this sketch, but I'll just mention this. Our cosine is going to be oscillating between y values of positive 1 and negative 1. Positive 1, negative 1. Positive 1, negative 1. And it's just going to keep on going. Now, in this point here, guys, again, it's not the best way to illustrate the cosine function, but it does get the point across. We're just going to keep on oscillating. And here's the deal. Since you're oscillating, you never really reach a particular number. So, if you do not reach a particular number, then you may remember that, in this case, the limit does not exist. Alright, now let's take a look at the next one here. So we have the limit as x approaches negative infinity for e to the x. Alright, so the e to the x, the natural exponential function, you may remember here that it is crossing the y value of 1, but it is a function that it is always increasing. So we should get something like this here. Now, because I'm asking you to figure out, hey, what's the limit as the x approaches negative infinity, as the x gets larger and larger all the way to the left, well then you're actually approaching a y value. You're approaching the y value of 0. So this particular limit is actually defined here. The limit is 0, so this one does have a horizontal asymptote, in this case being y equals to 0. Alright, so this is the first one that actually does have a horizontal asymptote. Okay, now let's take a look at the next one here. The next one is the typical rational function, 1 over x, the parent function for a rational function actually. Alright, so if I have 1 over x, you may remember. If not, that's okay. Hopefully it's a good refresher here. The 1 over x looks something like this. Now again, guys, this is not entirely accurate. I could be making better sketches, but it's just a sketch. I want you to remember how the graphs look like. Alright, so in this scenario, if we're dealing with this graph, as the x gets larger and larger, what is your y value getting closer and closer to? Well, it looks like our y values are getting closer and closer to y equals to 0. Okay, well, this limit here is 0, and once more, we do have another horizontal asymptote. Perfect. All right, now for the fifth example, we're going back to the exponential function. All right, so the e to the x, something like this here. Now this time around though, we're trying to figure out what's the limit as the x gets bigger and bigger. Well, this time around, your y value is also getting bigger and bigger. So this limit here is infinity, but you do not reach a number, so there is no horizontal asymptote. Okay, now let's talk about the inverse function for the natural logarithmic for the natural exponential function. Well, now we have the natural log, ln of x, where we made a sketch on the previous recording, and this one here is going to cross the 1. We know that the ln of 1 is 0, and it's just going to go and keep on increasing. Now for this one here, well, as the x gets larger and larger, well, your y values, they keep getting bigger and bigger as well. Now they're increasing rather slowly, but they're still increasing. You don't actually reach a number. So our limit as x approaches infinity for the natural log is infinity, and we do not have a horizontal asymptote. All right, now let's take a look at the next one. All right, well, we're back to the rational function 1 over x, where we know that it looked something like this here. And this time around, we want to see, hey, what is happening as the x gets larger and larger, but in the negative direction? Well, you get to see here that as the x gets larger and larger in the negative direction, we do seem to be approaching the y value of 0. So the limit is 0, which means that, hey, our horizontal asymptote is the y equals to 0. Okay, now, last but not least, or second to last, we're now going back to a natural exponential function. However, this one here, I'm actually going to do it in two different ways. The first one here is with a graph, just as we've been doing. Now, the graph of the natural exponential function, e to the negative x, because we do have a negative here, it just means that we're reflecting across the x-axis. So if our exponential function looked like this, that's e to the x, d to the negative x is reflected across the y-axis. So it should look something like this. Oh no, there we go. Okay, now what's happening here as the x approaches negative infinity? Well, as the x approaches negative infinity, well, we get to see here that our y values, they just approach infinity as well. So this one here is infinity. On the other hand, if I ask you, oh, okay, well, what would be the limit as x approaches positive infinity though? If you were to be approaching positive infinity, well, then you would have actually been approaching y equals to 0, but that's not the problem. All right, so this is one way of figuring this one out. Another way that I like to work on this one's here is playing a little bit fast and loose, but this is another way we can think about it. If we have the limit as x approaches negative infinity for e raised to the negative x, well, we can interpret it like this. And I'm going to go ahead and use, I wouldn't call it necessarily direct substitution, because we cannot do arithmetic with infinities, remember, but Well, we can kind of play fast and loose with it. I'm going to do this. I'm going to say that, okay, well, if I were to quote unquote plug in an infinity, I would get here a negative infinity here, which would give us here an e raised to the quote unquote here infinity. Well, what this is telling us is you're taking e and you're raising it to an arbitrarily large number. Well, that's just going to be infinity. There we go. Two different ways of doing it. Okay, now on to the last one. Now, the last one here, I'm actually not going to graph because, well, I do kind of know how this graph is going to look like, but not going to do a graphical approach for this one. Instead, I want you to think about what's happening. So for problem 9, we have the limit as x approaches negative infinity for the sine of x all over x squared. Now, what is happening to the sine of x as x approaches negative infinity? Well, I'm going to go ahead and reference our cosine graph. Remember that this cosine graph kept on oscillating between values of 1 and negative 1. Well, the sine function is also oscillating between values that are between negative 1 and 1. You cannot get bigger than 1 or bigger in the negative direction than negative 1. You're trapped there. So it's always going to be a number there in this particular interval, but what about the x squared? Well, if on the denominator you have an x squared and you let it be arbitrarily large, well, this one here is going to be an arbitrarily large number. So whenever you have a constant divided by something that is arbitrarily large, you would actually get 0. And if you don't believe me, that's okay. You can go to your calculator and start to divide 1 by numbers that are getting bigger and bigger and bigger. And you'll see here that indeed your y values are getting smaller and smaller, approaching 0. So this one here was a trickier one. Now we were able to get an answer here because I was not simply asking you to find the limit for the sine as x approach infinity or negative infinity. It was the sine over an x squared. So we had a constant divided by some arbitrarily large number. Now, some of you guys may be thinking, well, what happened to the negative? Well, what we basically had here was a negative infinity, and we were squaring it. So yes, it would have become an arbitrarily large number, but because we're squaring the negative, it became a positive. Okay. Hopefully this one here was a good review of some of the basic functions. But now, I want you to think about the following question. So we've seen that some of these graphs had horizontal asymptotes, but can we think of a function that could have more than one horizontal asymptote? Maybe 2 horizontal asymptotes? That's a good question. I'll let you think about some functions that we didn't cover right now, but you happen to know when they maybe have more than one horizontal asymptote. So let's go ahead and pause the video and see what you guys come up with. Did you come up with a function? One function that I'm thinking here is the arctangent function or the tangent inverse function. So if I have here y equals to the tangent inverse of x, well, this particular function looks something like this. It is kind of like a tangent function that's flipped or tilted to the side. And it actually does have 2 different horizontal asymptotes. To be specific, the horizontal asymptotes are y equals to a negative pi over 2 and a positive pi over 2. All right, perfect. Now, this video here is getting a little bit long, so it's actually going to be split into 2 parts. But to finish this video, I do want to discuss a very handy theorem. And this one here tells us the following. If you're dealing with a number r that's greater than 0, being a rational number, then the limit as x approaches infinity for 1 over x to the r is 0. Now, if r is greater than 0, and again it's a rational number, such that x to the r is defined for all x, then the limit as x approaches negative infinity for x to the r is also, for 1 over x to the r, is also equal to 0. And this is pretty much what we've been using without actually referencing the theorem. Anytime that you have a constant and you're dividing it here by some number that is getting arbitrarily large, either in the positive or in the negative, you are going to get 0. All right, so this is where we're going to be stopping here, and we'll resume on part 2. See you there.